Okay. I want to spend today doing integrals specifically of trig functions. So that formula sheet with the trig derivatives piece, have that at the ready. If you have your textbook, you can turn to the trigonometric derivatives, which are chapter 3, section 3. You can get on Canvas and pull it up there. We've got all sorts of places for it. I want to start with the Pythagorean identity for trig functions, the big one. Back in trig class, I said this is my favorite identity in the entire world for trig. Pythagoras. Pythagoras for trigonometry. The hell was this identity? The internet is your friend. Look it up. You may not remember it by this name. The most fundamental basic identity when we learned the unit circle. Exactly. Sine squared x plus cosine squared x is equal to 1. I'm going to make heavy use of this today and its variations, but I'm going to start with this one because I want to do an integral that I otherwise have no freaking clue how to do. I know how to do the integral cosine. Integral cosine is minus sine. I can do that. Cosine cubed? I can't do a u substitution. If I do a u substitution, what do I need? The derivative of cosine. Sine floating somewhere around it. There's no sine. If I try to do integration by parts, I don't have another part except the dx. And that would mean I would take the derivative of this would be the u part, so I get du is 3 cosine squared sine, and then I get an x, and that would make an x times a trig, which would be worse than this. There's no x in this right now. I don't want to do integration by parts. So I look at this and I go, what the am I supposed to do with this? Let's take 2 cosines away. Or really take one of them away and leave 2 of them behind. And now I go up to that top line and I say, oh, I know how to turn cosine squared into other things. If I rewrite this to get cosine squared all alone, I have cosine squared is equal to and all of a sudden I feel myself relax. I can breathe a sigh of relief. Because now I do have sines and cosines together. That's a u substitute. How would I set that up to be a u substitution? If I do that, u is the whole thing, then I need the derivative of that for the du. What's the derivative of this? That's got a chain rule in it, doesn't it? The one has derivative 0, so I get a -2 ugly thing to the first, and then the derivative of the ugly thing. So if that was u, do I have all of this for du? Ugh, damn. Not a bad idea. But when I say to myself, oh, look, all of this parenthetical expression is in terms of sine. And the only thing sitting on the outside is the cosine. I don't think I need to distribute. I think instead of distributing, I'll make the substitution right here with the idea to make this the du. What is cosine the derivative of? Sine. Just sine. So if I say, oh, I'll let u be sine of x, then du is cosine of x dx. I have a power rule problem. I know how to do that. I like power rule problems. Finish that out. If I had distributed, I would have the integral of cosine and then the integral of sine squared cosine. And I'd still need this same u substitution to do that second half. So I do it here without distributing. I saved myself a little bit of algebra that I don't have to do. What's my antiderivative? Well, no, be careful. If I go from here, I'm going to get u minus 1/3 u cubed plus c, but u is sine of x. So if I start in x and I end in x, I end up here. That. Just because we're in terms of u, I got to reset that same substitution back in. I said yesterday I was going to turn out my u substitution on steroids. I'm going to use these ideas a lot. I like this. But some of you are looking at me like I just slapped in the face of the fish. So what's going on? Talk to me. The trick to me at the start of this, the thing I noticed when I first set this problem up, was that I had a cosine cubed. And my Pythagorean identity is in terms of cosine squared. So I'd have one floating cosine left over. That gave me a hint for a du. Voice in the back of my head saying, there's an odd power here. Let's pull one item off that odd power. If I have one extra sign in this problem, throw that off to me. Hey, I'm going to play this same idea in my head, that extra thing off on the right. That's going to be my du, or related to my du. If the sine is du, what should u be? Well, but I could fudge the minus sign, couldn't I? I could just do u as cosine, and then I'd have a minus sign floating around that I need to adopt somewhere. So I should write, means I should write the rest of this in cosines. So how can I turn this stuff into cosines? So this is part of du. Well, again, I say to myself the same thing I said earlier. I've got Pythagoras on my side. If I want cosines, I get cosine alone in Pythagoras. What's the expression in Pythagoras when I get cosine alone, or cosine squared alone? 1 minus sine squared. But that's cosine squared x. Oh, that'd put everything in sines. I don't think that's the right way to go. Okay, let's do it the other way. We'll get sine all alone. Sine squared x is 1 minus cosine squared x. Okay, well, then I can get rid of the sines and put things, wait a minute, this is sine squared, this is sine to the fourth. Say that again? Just square it. Sine to the fourth would be 1 minus cosine squared squared. So over here, I have the integral of 1 minus cosine squared x all squared, then another cosine squared x, then a sine x, and a dx. If I let u equal cosine x, then du is minus sine x dx. I'm missing the minus sign, Emily. That's what you were pointing out to me earlier. So I'll move the minus onto the other side with the du. Now, I want to rewrite this integral in u. So what does this line become when I make this substitution? I don't laugh at people. Tell me which one's on. Well, yeah, this part will be a negative. Well, this part would be a negative du, absolutely. So I'll put the minus here and I'll put the du there. What about the middle? This part. Now, before you run screaming for the hills, we just multiply that out. So I square out the 1 minus u squared, and then I multiply the u squared in. If you want, you could multiply the minus sign in as well. And now take your antiderivative. It worked. But I'm not done. One more thing. But wait, there's more. I need to take my substitution, put it back in. Started this problem in X, I need to finish it in X. Since it's an indefinite integral, if it was definite, I could change the numbers, but I didn't do that. So I end up with, what was U? So we put everything back in cosine, minus 1/3 cosine cubed X, 2/5 cosine to the 5th X, minus 1/7 cosine to the 7th X. Let's see. Whew. Oh boy. Question. The key element, the pattern kick in my head, say, hey, do this, was that oddball power. I had an odd power of sine or an odd power of cosine. Rip one away and let's do something with it. So what if I don't have one? In addition, on canvas, where our trig derivative formula sheet was found, there's another formula sheet. It says trigonometric identities. If you took a trigonometry or pre-calculus course, I said repeatedly, we're only going to use some of these frequently. And the ones I remember the most involve the double angle formulas. Now, I'm the first person to tell you I'm bad at memorizing. I memorize as little as I can get away with and figure out how to take what I have memorized and turn it into other crap. There's a formula on that formula sheet that says square reducing formula. But what I remember is the double angle formula for cosine of 2x, which is cosine squared x minus sine squared x. So it's Pythagoras, but with a minus sign. Then I take the Pythagorean identity that we just had. Pythagorean identity we were just using, and I'm going to get rid of this cosine. And that makes this 1 minus 2 sine squared x. Take that formula and rearrange it to get the sine squared all alone. In the section labeled square reducing formulas, you will see that formula. I can never remember the sign in the middle, whether it's a plus or a minus. I always F it up. So I go through the process of remembering how to get it so I don't mess it up. If you would rather memorize this formula, go for it. There's also one for cosine squared. The difference is that plus in the middle versus the minus in the middle, and I will screw this up all the damn time. Somebody told me a little memory trick just last year that has started to sink in. When I see a sign, I'm going to subtract. I don't always remember it. But that means that I can actually solve this problem by getting rid of the square and ending up with something that doesn't have a square. So I'm going to finish this by doing this. Oop, dx. The over 2 is a 1/2. Let's pull it out front.
For the second one that you wrote down the formula, why is the cosine squared equal to 1 plus cosine?
Because if I do this process again, I will have cosine of 2x equals cosine squared x minus 1 minus cosine squared x. So I get 2 cosine squared x plus 1. So when I go to get rid of it, that sign changes.
Sine go. Did you just?
I replaced it with the 1 minus cosine squared. I'm starting from here again to get the new version in cosine squared. That's why the sign changes. Oh, that's a minus 1. So when I move it over there, it becomes 1 plus cosine 2x is equal to 2 cosine squared x. So that's 1 plus instead of 1 minus. We'll walk through it in a minute. What is the antiderivative of 1? That was easy. Oh. Aha, to do the cosine of 2x, I need a u substitution, don't I? Do I have a 2 next to my dx? 1/2 du equals just dx. So I get the integral of 1/2 cosine u du. It's the integral of cosine u. The integral of cosine is sine. I wrote too many pens dry apparently this week. 1/2 x minus 1/2 sine. Oh, it's going to be sine u, right? But u is 2x. We'll see.
The one half on the outside of it, and the other second one on the inside.
Well, I'm only pulling it to the outside of this integral. Yes, because I did the integral of 1 and I got an x. I did the integral of the cosine all the way over here separately. I really did do 2 separate integrals. If I bring those 1/2s together, I get 1/2 x minus 1/4 sine 2x. Let's see. Questions? Emily, you're still unhappy about this. So let me go back up here for a second.
Can you back place, you go from sine to cosine, because down there you just wrote cosine over, and I'm still wondering where the sine. I know you converted it somewhere, but I'm really bad at trig, and I understand that that's part of this entire thing, and I need to know where the sine went.
The sine went from here to here.
Okay, so you just use the formula we used before with prior, and you.
Yep.
Changed it.
Yep.
Thank you.
I want Pythagoras to be my best friend, lives in my back pocket. Questions? If I have an odd power, I'm going to strip one piece off. So if I have cosine to an odd power, I'll strip off one cosine. My substitution will be u equals sine. If I have an oddball odd power of sine, I'll strip off one sine. My substitution will be cosine. If I have no odd powers, I'm going to use these double angle formulas. There's one other double angle formula, and that only shows up if my powers happen to be equal. Because these all came from cosine of 2x. Does anybody remember the formula for sine of 2x? This is why there's a formula sheet there. 2 sine x cosine x. Which means if I have the same power, I might be able to make my life easier that way. And then only end up with one trig function. An example. There's no odd powers. This is going to suck. No, we can fix this. I'm going to take this and write it as sine x cosine x squared. So now I look at this. Be careful. I bring that 2 to the other side of this first. Sine x cosine x is 1/2 sine 2x. Which makes this 1/2 sine 2x squared. Well, there isn't a 2 here, right? So I moved that 2 from this side to this side to give me this 1/2. So that's where this comes from. Because yes, you're exactly right. I'm missing a 2 somewhere. I have to account for it. I don't have to shove it in. What I could have done is I could say, all right, I'll put a 2 in front of each of these, and then I'll put the corresponding 1/2s out front. But I put it inside instead. But if I'm going to square this whole thing, then I should square the 1/2. What's 1/2 squared? That goes out front. Well, now I'm happier. Well, that's a relative thing. I'm less pissed off. Sine squared. I know what to do with sine squared. I just got a formula for sine squared. What do I do with the sine squared thingy? I do this. Only there's already a 2x in here. So what happens over here? I get a 4x. And now there's another 2 I have to deal with. So let's throw that out here. And we'll make this 1/8. 1 minus cosine 4x dx. Emily, this time I will explicitly spread the two integrals apart. So I have the integral of 1 minus the integral of cosine 4x dx. Each of them goes from 0 to pi over 2, and each of them has the 1/8 in front of them. The first integral is a piece of cake, but the second one, what does it require? Ta-da! I know what to do. As I said yesterday, my goal is to take that doesn't look right and turn it into stuff I do know how to do. I have to go back to the patterns I already know. So over here, u is 4x, du is 4 dx. I don't have a 4, so I'll get a 1/4 du to be my dx. And to make my life easier, what can I do here? Yeah, what can I do here? I can change the bounds into u. If x is 0, 4 zeros is still 0. If x is pi over 2, 4 times pi over 2 is 2 pi. The antiderivative of 1. That should not silence the room, people. You should all know that one. The antiderivative of 1 is just an x. Yep, 1/8 x 0 to pi over 2 minus 1 over 32. What is the antiderivative of cosine? Sine of u from 0 to 2 pi. So here I get 1/8 times pi over 2 minus 0 minus 1/32 times sine of 2 pi minus sine of 0. What is sine of 2 pi? And sine of 0. Woohoo! Everything else in there is a 0. So I have now increased the list of things I think you should remember to add some trig formulas, some trigonometric identities. Pythagoras and the two double angle formulas. If you want the square reducing formulas, they come from the double angle formula for cosine, but you're welcome to add them too. I can't get those in my head straight. I always have to derive them. Double angle formulas, they stuck. Square reducing ones, I keep picking them up. I'm giving you the formula sheet. I know is trig derivatives. That's the calculus formula sheet. Trig identities are prerequisite. And that means you should have a flashcard. Something you can start thinking about. Make the list of things you need to have in between your ears now. And these 5 go on it. Or at least 3 of them. Questions?
Could you please write or tell me the three?
Pythagoras. The double angle formula for sine. The double angle formula for cosine. If you want the square reducing formulas, you can get them from these 2. Or you can try and jam them in there. Sine squared x is 1 minus cosine 2x over 2. Cosine squared x is 1 plus cosine 2x over 2. More questions? Yeah.
Or substituting for another. Like what's?
The whole reason we're doing this is to do weirder integrals. Oh, absolutely. So my first reaction is to look at the integral that was provided to me and say, what do I know I can do with this integral? I don't know how to find that antiderivative off the top of my head because it's an even power of cosine. There's no oddball there, so I can't do the easy thing and strip an odd power out. I do know cosine squared. So cosine to the 4th is cosine squared squared. Aha. Cosine squared is right here. Ooh, I forgot my dx. But that needs to be squared out, right? Because it's cosine squared squared. Oh, man. All right. So I take the denominator. 2 squared is 4. So there'll be a 1/4. And then I'll have 1 plus cosine 2x squared. Square out a plus b. And I get 1 plus 2 cosine 2x plus cosine squared 2x, which means I have another cosine squared, you mother. All right. So I have to do this formula again for the cosine squared, but now it's cosine squared 2x, which means it's going to become, say it louder, a 4x. So what I really have is three different integrals here. I'm going to have the integral of 1.5. Then I'm going to have 2 cosine 2x. And then I'm going to have an eighth cosine 4x. This was the same double angle formula, the same square reducing formula, twice. That first integral I do trivial. How do I do the second integral? Pull the 2 out, and then I use substitution. What do I do here? A different u substitution. Here I do u as 2x, here I do u as 4x. But I turn stuff I have no clue how to do into things that are now, oh, that's a u sub. That's last semester. I remember that. I hope.
You did. Substitution of science squared.
Yeah, I did one from here to here, and I did one from here to here. Just like my integration by parts, I needed to do the same trick again.
Sine. Sine.
I didn't have a sign anywhere in this problem. Well, then I would have ended up with even powers of sine, right? I would have had to use the sine squared formula, right? Because I have sine squared and sine to the fourth instead of cosine squared and cosine to the fourth. So the fact that this problem, no matter which set of substitutions I want to play with, I'm going to get stuck with even powers, and even powers are, so I'm going to use this double angle reduction somewhere. Leave yourself about 3 more lines. You should be able to finish this problem. It's just u substitution. More questions. Page 495, box. If you've got an odd power of cosine, pull 1 cosine off. If you've got an odd power of sine, pull 1 power of sine off. If the powers are both even, here are our square reducing identities. Sometimes, if the powers are equal, we should use the sine version. Page 495. There's just one problem. There's 4 more trig functions. Secant, cosecant, tangent, cotangent. All right, wait a second. Pythagoras. I want you to take everything there and divide it by cosine squared. So I'm going to get sine squared over cosine squared. Then I'm going to get cosine squared over cosine squared. And then get 1 over cosine squared. Wait a minute. Sine over cosine. That's another trig function. Which one's sine over cosine? Tangent. Cosine squared over cosine squared is 1. What's 1 over cosine? Secant. So 1 over cosine squared is secant squared. There's another Pythagoras, which relates secant and tangent. Hey, wait a minute, look at the derivatives. What's the derivative of secant? You have a formula sheet. No, that's what secant is equal to. What's the derivative of secant? It's secant x times tangent x. What's the derivative of tangent? Secant squared. So if I see secants and tangents, I can do this sort of thing and do a u substitution in secants and tangents. It's going to work. I can do the same game we played of pulling out either 2 secants and then having u be tangent, or I can pull out 1 secant and 1 tangent and have u be secant. Holy shit. If I see secants and tangents together, their derivatives go together like sines and cosines do. That's going to make my life easier. And the other two group together like that. If I take this same Pythagorean identity and I divide by sine squared x instead, then I get sine over sine, cosine over sine, and 1 over sine. So there's a Pythagorean identity that relates cosecant and cotangent, which means just like secants and tangents, and just like sines and cosines, if I see cosecants and cotangents together, I can do this same game. Page 496. If I have 2 secants, I can strip 1 pair off, turn everything into tangents, and make my life easy. If I've got an odd tangent with a secant, I can make a secant and tangent, and then my u is going to be everything in secants. But that means floating around somewhere, I need one more derivative rule. I need to know, one more integral rule. I need to know the integral of secant of x. I know how to do the integral of tangent. I know how to do the integral of cotangent. I don't know how to do the integral of secant. The integral of secant's an oddball thing. And I'm going to steal this trick. I would never have thought of this on my own. I read it and I've remembered it. And I say, this is the way to do the integral of secant, is to multiply by 1. But the 1 I'm going to multiply is secant x plus tangent x over secant x plus tangent x. And I agree with you. You should look at me and go, you've got to be out of your mind. Because I had no idea where this came from. Until we rewrite this. 1 over secant x plus tangent x times, take the secant here and multiply it with all of those things on top. Secant squared x plus secant x tangent x. Now, are you ready for the craziest thing in the world? This is the derivative of this. Secant times secant in the numerator.
Oh, so you just-
I just distributed this into these two. The derivative of tangent is secant squared, and the derivative of secant is secant tangent. This is a U substitution. What's the integral of 1 over u? Which means I get ln of secant x plus tangent x plus c. I am the first person to tell you, I will not be able to memorize this formula. I will give you that formula. There's another one for cosecant. I'll give you that one too. The integral for secant is the top of page 497. The integral for cosecant is not given in the textbook, but will be provided to you. It's in the back of the book in our giant set of tables that we'll look at later this week. Next week. Everything I did for secant and tangent, I do for cosecant and cotangent. It's just harder because secant and tangent are not ones we use all the time. Sines and cosines I'm much more comfortable with. Secants and tangents you use them. So if I can, I'm going to put things in sines and cosines as often as I can get away with it. And that's helpful. There are lots of other trigonometric identities I can pull in. That's what that formula sheet is for. Questions? I will see you all on Monday. Have a wonderful weekend.